In section 9.2, we discuss quadratic functions. This video will be working problem number 26 from your homework, which is found on page 556. The learning target for this section is I can graph quadratic functions of the form y equals ax squared plus bx plus c. Let's keep in mind the key idea from this section. In the quadratic function y equals ax squared plus bx plus c, the value of b translates to the position of the axis of symmetry. So when you're looking at these functions and you look at the value of b, which is here, that value is going to translate to the position of the axis of symmetry. As a matter of fact, we have a formula which helps us to go from the function itself to the axis of symmetry of the function, and that is that x equals negative b over 2a. If I take the value of b from the function and I negate it and then divide it by 2 times a, that will give me an equation for the axis of symmetry. Now, since the axis of symmetry is always going to pass through the vertex, it will also give me the x-coordinate of the vertex. So the x-coordinate of the vertex and the axis of symmetry are very closely tied together. So look at the problem. A baseball is thrown into the air with an upward velocity of 30 feet per second. Its height, h, in feet after t seconds is given by the function h equals negative 16t squared plus 30t plus 6. How long will it take the ball to reach its maximum height? What is the ball's maximum height? And what is the range of the function? Now, if you take a close look at the function that you're given here, notice the number 30 that is part of the linear term of the function. Where does that number come from? Well, if you look up here where it said upward velocity of 30 feet per second, that number 30 actually comes from the upward velocity of the ball. So in other words, when the ball is thrown upwards, the person that is throwing the ball is going to put a force behind it that's going to give it an initial velocity. And that number 30 feet per second, that's how fast it's traveling when the ball leaves the hand of the person that throws it. Now remember, it's going to be going upward. So gravity is going to be playing a part in this as well. So as the ball goes upward, it's going to actually slow down and it's going to get to a maximum height. And once the ball reaches a maximum height, then the ball will start to fall again. So we get a diagram that looks very similar to this particular diagram that I've got on the board, where the baseball pitcher or the person throwing the ball is throwing it upward, it reaches a maximum height, and the ball then starts to travel back down toward the earth. What we're looking for then is, well, how long is it going to take to reach the maximum height? So if this is the maximum height here, then how long does it take for us to get there? And then we also want to know, well, what is that? How high up does the ball actually go? Well, to solve this problem, the first thing we're going to do is actually draw a graph that depicts the function. This will give us a better idea of what the numbers look like. Okay, so I'm going to draw a grid here. So I just need an x and y axis. But in this case, since my function is h is equal to negative 16t squared plus 30t plus 6, I'm not going to use x and y. I'm actually going to use t and h as my axes. And t represents time, so I'm going to label that. And h is going to represent height, so I'm going to go ahead and label my axes. Well, when we're graphing these functions, the first thing that we usually like to do is to find the vertex. So that's what I'm going to do first, is look for my vertex. Remember, my vertex will have an x-coordinate and a y-coordinate, which in this case is a t-coordinate and an h-coordinate. And to find the vertex, the x-coordinate of the vertex, I actually use the same formula that I used to find the axis of symmetry, and that is x is equal to negative b over 2a. But remember that even though the formula says x is equal to, what I'm actually going to be doing is solving for t. So I'm just replacing the x with a t value. And then I plug in For b, I'm going to put in 30, so that gives me negative 30 over 2 times negative 16. And if I plug that into my calculator or however you solve it, this is going to be the same thing as 15 over 16. And that tells me that the x-coordinate of my vertex is in fact 15 over 16, which is not quite 1 second. It's just slightly less than 1 second. Now I'm on my way to getting a graph of this, but I need now the h component of my vertex, which corresponds to a y basically. So I'm going to plug in 15 over 16 back into the original function like so. And again, you'll want to use a calculator for these problems. You don't have to, but it does help you get the numbers. And in this case, if I plug that into a calculator, I'm going to get 321 over 16, which is the mixed number 20 and 1/16. So that tells me that the h-coordinate of my vertex is 20 and 1/16. So let's graph that. So for my time axis, the vertex is not even quite at 1, so I'm going to put a 1 here and a 2. So in other words, the ball is not going to be in the air for that long. Then for the height, I need to have a maximum height of 20. So the ball is only going to go up to about 20 feet. So I think I'll use a scale of 5 here. So 5, 10, 15, and then there's 20. So now I've got a scale chosen, and notice that I used the numbers of my vertex to help me get that scale. So let's graph the vertex point. Where would 15 over 16 be? Well, again, it's just slightly less than a second. So about right there, and then I want to go up to slightly more than 20 feet, so my vertex point would be sitting right there. And now again, that vertex tells me the maximum height because the ball is going to go up, it's going to reach its maximum height, and then it's going to fall back again. But if I wanted to, I could probably stop right now and I could answer the questions that they gave me. How long will it take the ball to reach its maximum height? Well, 15 over 16 seconds, which is not quite 1 second. Then they asked me, well, what is the ball's maximum height? Well, I know that now it's going to go up 20 and 1/16 feet. So I can answer those questions. But they asked me a third question here, which is what is the range of the function? And to depict the range, I'm going to actually complete the graph of this function so that you can see it a little bit better. So let's block this off, and let's work a little bit more to get the rest of this function. Well, when the ball starts out, before you actually have the player throwing the ball, the time is going to be 0. And at a time of 0, I want to know, well, what would my height be? So if I put in a 0 in for t, what height would I have? Well, negative 16 times 0 squared is 0, and 30 times 0 is 0. Then I have 6. So my height would be 6. So that tells me that my y-intercept is 0, 6. Well, notice that that actually corresponds to this value here. So the c value is going to be your y-intercept. And now let's think about the symmetry of the graph. Remember that when you used x equals b over 2a, you found the x-coordinate of the vertex, but what you also found was the axis of symmetry. The axis of symmetry is x is equal to 15 over 16. And what that means is that the distance from the axis of symmetry to the y-intercept, this right here, is going to be equal to the distance to another point, the reflection point. I just need to know, well, where would that reflection point be? And I've got a nice graph of the function. So to do that, I just want to take 15 over 16 and add another 15 over 16 to it, which is 30 over 16. And 30 over 16 is the same thing as 1 and 14 over 16. So that tells me that 1 and 14 over 16, 6 is a reflection point. So that would be about right there. And that gives me the graph of the parabola, like so. So let's think about what the problem then is saying. The baseball player, who was probably about 6 foot tall, throws the ball up in the air with an initial upward velocity of 30 feet per second. So the ball starts to travel up. As it's traveling up, it's losing its speed till it reaches a maximum height. What is that maximum height? About 20 feet, 20 and 1/16 feet. How long does it take it to reach its maximum height? Almost a second, about 15/16 of a second. It reaches its maximum height and then the ball starts to fall. How long does it fall? Well, after another 15/16 seconds, the ball is going to be back at 6 feet. That's how that reflection works. Will the ball continue to fall? Yes, the ball will continue to fall because there's nobody there to catch it. So the ball continues to fall until it hits what? It hits the ground. And the ground here is this axis, 0 feet, a height of 0 feet. Knowing this will enable us to answer this question: what is the range of the function? The range of the function is all of my height values. In other words, what possible values are we allowed to have for the height? Well, the lowest height that I can have is 0, because the ball is never going to get below the ground. But what is the highest height value? Well, the highest the ball will go is 20 and 1/16 feet. So my range then would be 0 is less than or equal to h, which is less than or equal to 20 and 1/16 feet. In other words, my height will always fall somewhere between 0 and 20 and 1/16. Okay, so let's write out our answers. Okay, so we know that it's going to take the ball 15/16 of a second to reach a maximum height of 20 and 1/16 feet. The range of the function is the lowest height, which is 0, is less than or equal to the highest height, which is 20 and 1/16.